Hi there, welcome to Solutions Part 2. We're actually going to, for today's lecture, we're going to break it into two parts. So the first part, we're going to talk about enthalpy and being able to predict the signs of enthalpy, understanding how enthalpy is going to relate into the formation of a solution. Let me just share this real quickly with you. So we're going to understand enthalpy as it relates to a solution. We're going to learn the steps for solution formation and be able to predict the signs of enthalpy, and then we're going to apply it specifically to ionic compounds. So aqueous chemistry is a huge field just because a lot of reactions happen in an aqueous environment, including most of the reactions that happen in our body. And so aqueous chemistry is a large area of study, and one that we're going to focus on a lot in the second half of the book. And so we're going to apply this idea of enthalpy specifically for ionic solutions, and we have a couple of different types of equations that we can apply to that. So that's what we're going to learn in this first part of part 2. And remember that we're not going to be doing example calculations with you in these lectures. These lectures are really more conceptual, and then our Zoom meetings when we meet together, that's where we're going to do these problems. And so the calculations that would be involved with this material is going to be something that we'll do in our Zoom session. You can find all the problems that we're going to do together in the lecture problem worksheet or also on our weekly materials. So let's just do a little bit of review here. All right, so we left off, we were talking about intermolecular forces, and so most solutions involve intermolecular forces, so that's why it's really important that we kind of establish that. So most solutions involve intermolecular forces, except for solutions that have gases. And because gas molecules do not have intermolecular forces between them, then a solution of gas is really not going to be driven by or affected by intermolecular forces. Gas solutions are driven solely by entropy. And remember, entropy was our measure of disorder. Any system or any process or any chemical reaction that increases the amount of entropy, increases the amount of disorder, increases the amount of movement that molecules have, is going to be favored from an entropy standpoint. And so the formation of a solution of gases is always going to be favored. It's always going to be spontaneous because you're always increasing the entropy. Always favored. And this is only for gases. And so there's two components that drive the formation of a solution: entropy. And entropy is always going to be favored because if you form a solution, you're always increasing the amount of disorder or dispersion that's happening. And so entropy is always going to favor a solution. Because gases have no intermolecular forces, the only thing that's driving it is going to be entropy. Solutions of liquids and solids, entropy is still going to favor it, so it's going to be favored by entropy, but it's also going to depend on enthalpy, and this is where these intermolecular forces are going to come into play, is this enthalpy component. And so the enthalpy is really looking at what is the energy that's happening when we have to break intermolecular forces and when we form intermolecular forces. And so if we have anything other than a gas with a gas, now we have to consider enthalpy. And so this is H. And so H is not always going to favor the reaction, unlike enthalpy, where entropy is always going to favor the reaction. Enthalpy may or may not favor. So may or may not favor the formation of a solution. So we're going to look and see what are the conditions where enthalpy will favor the formation of a solution, and what are the conditions where enthalpy will not favor the solution. And then the magnitude between enthalpy and entropy will determine whether your solution will form or not. So if I have something that's really significantly unfavored from an enthalpy standpoint, even though it's favored from an entropy standpoint, that solution is not going to happen, and vice versa. So my steps to form a solution are this. From here on out, we're really not going to talk about gases because gases will always form solutions. So this is going to be a discussion where we have to consider enthalpy. Steps to form a solution. And we're going to omit gases from here. Okay, so step number 1 is I have solute solute. So remember, there's two components of a solution, the solute, which is the minority component, and the solvent, which is the majority component. So I have to overcome the intermolecular forces between solute molecules. So I have to overcome that intermolecular force that's holding those solute molecules to each other, right? Because in order for them to go into a solution, I have to break them apart essentially first. I have to also, if I look at solvent molecules also have intermolecular forces between them. So I also have to overcome the intermolecular forces between the solvent molecules. So both of these steps are going to require energy. So both of these steps are going to require energy because I have to overcome those intermolecular forces. And the stronger those intermolecular forces, the more energy I have to put in. The third step is I'm going to form solvent intermolecular forces. So I'm actually going to form intermolecular forces between solute and solvent when I form the solution. And this is energetically favorable. So this releases energy. So this I'm going to have to put energy in, this I'm going to have to release energy. And so if I look at the heat, whether that solution is going to form or not, I'm going to look at these factors. How much energy do I have to put in, and how much energy am I going to get out? If I have to put energy in, then that's going to be positive, right? Because I'm putting energy in. If I'm releasing energy, that's going to be negative. So this is going to be favored. These are unfavored. So unfavored and favored. And it's going to depend. If I get more energy out than I have to put in, then chances are that solution is going to form. If I have to put more energy in than I get out, then chances are that solution is not going to form. And so looking at these individual steps are going to allow us to determine what's going to happen. And so we have a way of talking about this energy. And so this energy in solution formation is enthalpy, delta H of the solution. So we write it that way, or we could write it delta H SOLN, which is short for solution. So that's how we're going to track these intermolecular forces, right? What the energy is, either I'm forming them or I'm breaking them. So my delta H then here, this is going to have a delta H of a positive because that's energy I'm putting in to break these guys. This is going to have a delta H of positive because this is energy I'm putting in to break this intermolecular force. And this delta H is going to be negative because this is energy I get out when I form this new intermolecular force between the solute and the solvent. We have an equation for this, of course. This equation looks like this. Keep track of all these energy, all these intermolecular forces that I'm having to break or I'm forming. So my delta H of my solution, my overall heat of that solution, is going to equal the amount of energy I have to put in to break the intermolecular forces of the solute, plus the amount of energy that I have to put in to overcome the intermolecular forces for the solvent, plus whatever energy I'm going to get out when I form my solution. So that's my mix. So I'm going to call this solute. This is my delta H of solute. This is my delta H of solvent. And this is my delta H of mix. And so my heat of solution takes into account all three of these components. These two that require energy, and this that is going to release energy. So my sign, if I look back to that equation here, if I think about the sign, so the sign of this is always going to be positive because that's going to require energy. I'm going to have to put energy in to break those solute-solute bonds. Intermolecular forces, not really bonds. The sign here is also going to be positive. That's going to require energy to break apart those solvent molecules. My sign here for delta H mix is always going to be negative because that's the energy that I get when I form those new intermolecular forces. So here I'm going to release energy. And so my sign for overall is going to depend. It's going to depend on the magnitude of this, the magnitude of this, and the magnitude of this. So if we think about it, if my delta H of my solute, delta H of solute plus my delta H of solvent is greater than my delta H of mix, then my delta H of solution is going to be positive, and chances are that solution is not going to form. So that would be one scenario. If my delta H of my solute plus my delta H of my solvent is less than delta H of mix, now my delta H of solution is going to be negative, and it's going to be favored from an enthalpy standpoint. I could also have this scenario, plus delta H of solvent equals delta H of mix. So in this case, my delta H of solution is going to be close to 0. All right, so this is not favored. This is favored, meaning that the enthalpy component of that solution is not favoring the formation of it, right? Because it's going to take more energy to break the intermolecular forces than you're going to get when you form new intermolecular forces. Here it's going to be favored, so in this scenario, your solution will form. Here, you don't know. Solution may or may not form, because remember, you also have entropy. So here, if I really don't have much of a change in my intermolecular forces, where my delta H of solution is 0, this is going to be favored because my entropy component will favor that. Neither favored nor unfavored from an enthalpy standpoint, but it's going to be favored from an entropy standpoint, S. And so this one will form because it's favored from an entropy and an enthalpy standpoint. This one may or may not form because it's still going to be favored from an entropy standpoint, but it just depends on the magnitude here. So in chemistry, we do a lot of things in an aqueous environment. And aqueous means that I have an ionic compound in water, right? So I've formed a solution. That solution, I've taken an ionic compound, it's been able to solvate in water. That is my aqueous ionic. And if I write NaCl, for instance, with AQ here, that implies that I have sodium chloride is dissolved or solvated in water. And so that would be my shorthand for writing an aqueous solution. So we can kind of simplify our reaction here specifically for an aqueous solution, for what's happening in an aqueous solution. I'm going to combine some of these terms, right? So I'm going to look at these two terms here. I'm going to look at solvent and mix. And then I'm going to look at this term independently for my ionic compound. Before I do that, let's just go back to the slides real quickly. This slide here. So this kind of sums up sort of what we just talked about. So in order for this to form, I'm going to have to break these solute-solute interactions. I'm going to have to break my solvent-solvent interactions, and then I'm going to form new solvent-solute interactions. And so it's this interplay between these three types of energy. This requires energy, this requires energy, this is going to release energy that's going to determine the magnitude of the enthalpy, the heat of that solution. And so I'm looking at these three components here. If I take an ionic compound, and I dissolve an ionic compound in water, I first have to break apart that ionic lattice. So now I have ions. So remember, sodium chloride as a solid is a packing of sodium ions and chloride ions, and they're packed together in that lattice structure where you have alternating positive and negative charges. And so in order to form an ionic compound in water, I'm going to have to first break apart that ionic lattice. That's my solute, my heat of solute, breaking apart those. I also have to break apart the hydrogen bonding that's happening between the water molecules, and then I form this ion dipole intermolecular forces here, where one of these ions is going to be completely surrounded by the polar ends of the water molecule. And so if you think back to the intermolecular forces, go back to that slide. We think about the magnitude here. I'm overcoming this hydrogen bonding in my solvent to form ion dipole in the solution. So if I just look at what's happening in the solvent phase of things, I have to break apart the solvent intermolecular forces, and then I'm going to form solute solvent intermolecular forces if I have an ionic compound, it's going to be this ion dipole. So this is always greater than this. And so for an aqueous solution, we could kind of do a little bit of a shortcut here and combine these things together here. So this would be my solvent intermolecular forces, and this is my solute solvent intermolecular forces that I'm forming. For an aqueous, this is hydrogen bonding that I'm overcoming, and I'm forming ion dipole. This is always going to be greater than this. So this is always going to be less than this. So if I combine these together, I'm going to expect a sign that's going to be negative, right? Because I'm gaining energy by taking my solvent intermolecular forces, that's hydrogen bonding, that's the energy I'm putting in to break apart those water molecules. I'm gaining more stability when I form an ion dipole because that's a stronger intermolecular force. And so this is always going to be greater than this for an ionic compound. So I can combine these two together, and I'm going to call this the heat of hydration. And that is always going to have a negative sign, okay? Because the bonds I'm forming or the interactions I'm forming are going to be greater than the ones that I have to break apart. So my heat of hydration for an ionic compound. And then my delta H of my solute, I can refer to that as the lattice energy. And we'll talk about why that's negative, but this is always going to be a positive value here. So let's talk a little bit about lattice energy, and then we'll come back to this heat of hydration and pulling all of this together. So remember lattice structures. When I form a lattice, so if I have sodium chloride solid, this is an ionic structure where I have sodium ions and chloride ions that are packed together in this alternating crystal structure here. And these are very stable because you have each of these ions. If I look at sodium ion here, sodium ion is surrounded by the negative chlorine ions. And so it's no longer just a one-to-one association. When you form this solid ionic compound, you have this uber stability here because each of these sodium ions feels a negative, an electrostatic attraction to the negative chlorine ions. Each of these chlorine ions is surrounded by sodium ions, and so it's feeling the electrostatic attraction to each of these sodium ions, and so that adds it some stability, and we call that the lattice energy. And this is the energy that's released when you form this ionic solid. So it's a negative value because it's energy that's released. So if I look at delta H lattice, that's going to be a negative value because if I look up lattice energies, those are always going to be negative because this stabilizes all of these ions and it releases this energy. So for an ionic compound, I have to overcome that lattice energy to break this thing apart, right? So my delta H of my solute then is going to be the negative of the delta H of lattice because this is inherently already negative. So if I take the negative of a negative, that's going to give me a positive value because this is an energy requirement. So don't get confused because if you look up lattice energies, they're always going to be negative because they're favored. Right? When you form a lattice, you're favoring that. It's adding stability to all of those ions. So if you pull this into our heated solution and you want to apply it, I can look up lattice energy values. If I take the negative of that negative, that's going to give me a positive. That's going to be the energy that I have to overcome to form this ionic compound, right? To take this ionic compound and form a solution with it, because I'm going to have to break apart all these intermolecular forces that are happening here between all these ions, right? And these are large, this is a large value. So that's why not all ionic compounds are soluble in water, because as their lattice energy increases, this increases, and it can't be overcome by your heat of hydration. So when this is really large and when this is larger than this, then you're probably not going to form a solution. So I'm going to rewrite this equation with all of these components here. So delta H of solution then equals delta H of my lattice. And remember, I'm going to make that a negative, plus delta H of hydration. So this is my solute here. This is going to be positive this is going to be negative, and this is going to depend right on the magnitude here. This is my solvent plus my mix, if you remember. So I could write it this way, or I could write it this way. So for ionic compounds, sometimes you see it written as lattice energy, sometimes you just see it written as delta H of the solute plus delta H of hydration. So both of those mean the same thing. This is still going to be positive, this is still going to be negative, this is still going to depend. So I could write these are equal to each other. Just two different ways of writing it, and these are obviously the same. Okay, so let's look at these from a scenario standpoint. Scenarios. So scenario number one, let's say I have delta H of solute is going to be less than delta H of hydration. My delta H of my solution is going to be what sign? Right now I'm going to predict the sign. All right, so I want to predict the sign. So this, remember, is going to be a positive. This is always a negative. So if this is greater than this, then this is going to be a negative, and this is going to be exothermic. That means when I take that ionic compound and I drop it in water, I'm probably going to feel, if I'm holding the test tube, it's going to feel warm because it's going to release energy. It's going to release because it has excess energy, because the heat of hydration is going to be greater. So that energy is going to go from the solute and the solution into kind of the atmosphere. All right, I'm going to feel it. It's going to feel warm. So this is going to be favored. This is going to favor solution. So if you have an exothermic process, you're going to favor the formation of a solution from an enthalpy standpoint. And remember, it's always already favored from an entropy standpoint. So this, you will have, your solution will happen. Okay. So let's say I have scenario number two, where my delta H of my solute is greater than my delta H of hydration. So my signs here are always going to be the same. This is positive, this is negative. Now my delta H of my solution is going to have a positive value. So this is endothermic. If this ionic compound does go into water and dissolve, the container that it's in is going to feel cold because it's going to be absorbing heat from the atmosphere. So this is going to be unfavored formation of solution. Unfavored from an enthalpy standpoint, but still favored from an entropy standpoint. So you can have this be positive and still have your solution form if the entropy is large enough to drive that. And then the third one is delta H of the solute equals delta H of hydration. This is going to be a positive, this is a negative. Now my delta H of solution is equal to 0. So this is neither endothermic or exothermic, so you're not really having an energy exchange. This is going to be neither favored nor unfavored from an enthalpy standpoint, but that solution is still going to happen because it's favored from an entropy standpoint. And so this will depend. This is our scenario where I'm not sure if that reaction is, or that solution is going to form. It's just going to depend on the magnitude here that's happening. All right, so that's where we're going to end this part of part 2, and then we'll come back together in a little bit and talk about solutions and concentrations.